Welcome to the JWST Town Hall meeting. I am Hashima Hassan, the JWST Deputy Program Scientist at NASA Headquarters, Washington, D.C. The Town Hall will feature speakers from the JWST Program Office at NASA Headquarters, the JWST Project Office at Goddard Space Flight Center, and the Science and Operations Center at the Space Telescope Science Institute, Baltimore. The presentations will provide the astronomical community with a status update of the mission, discuss the next steps in the commissioning timeline, inform the community on when to expect to see the first science data, and look forward to the first year of exciting JWST science. The talks will be followed by a question and answer session. The public may enter questions through the portal provided in the event announcement, and which is also displayed on the screen on the left-hand side. All participants will be muted. The meeting is being recorded. I would now like to request our first speaker, Dr. Eric Smith, the JWST Program Scientist, to make introductory remarks. Eric?
Thanks, Hashima. So we've been doing these town hall meetings for many years now, and typically at the start of these things, we get up and talk a little bit about the schedule and the risks ahead of us. And thankfully, those kind of presentations are no longer needed. As Hashima said, today you'll hear about how the observatory is actually operating. But before we hear from the project science team, what I wanted to do is actually just show you the project science team. Of course, if we were in person, you could see them wandering around the meeting, and I would encourage you to thank them in that case. And so that's what I really wanted to do today, was to thank this group of dedicated individuals, many of whom have worked behind the scenes for literally decades to bring this observatory where it is today on the science side. Of course, the engineering team has done just a marvelous job, and I'm sure you've heard all about that if you've been following it, and you'll even hear more about it today from the team. But it has been this perhaps unsung group that has helped make this observatory the amazing facility it's turning out to be. Of course, many of you know John Mather. Dr. John Mather is the senior project scientist, and Jonathan Gardner is his deputy senior project scientist. But you see, we have individuals who've been working on specific components of the observatory for many years, such as the instruments, Matt Greenhouse and Bernie Rauscher, the observatory itself. These days, it's Mike McElwain and Aaron Smith, but Mark Clampin was in that role previously. Chuck Bowers has also been critical. We have on the commissioning and instrument and test side, Randy Kimball and Chris Stark, who are doing an amazing job as we get ready to do science. And we are just about to come into operations, and there, Jane Rigby and George Sonneborn and Susan Neff made sure this facility will be all that you need it to be. And of course, Mal Niedner has helped us out in years in the past. We also have some project scientists specifically for disciplines, exoplanets, Nicole Colon, planetary science, Stephanie Milam. They've done an incredible job reaching out to those communities. And of course, you hear about all of this because of the hard work of Amber Strawn, who helps us communicate our message. So although you won't get to see them because we're not in person, I encourage you to email these folks and thank them for the amazing job they've done for many years getting this observatory ready. And with that, I'm going to turn it over to one of them, Dr. Jonathan Gardner, to tell you about Webb. Thanks, Hashima.
Thank you, Eric. So our next speaker is Dr. Jonathan Gardner, the JWST Deputy Senior Project Scientist at Goddard Space Flight Center, and he will give us the JWST mission update. John?
Okay, thank you, Hashima and Eric, for that introduction. I hope you can see my screen. I will move on to a very brief introduction. Webb almost needs no introduction at this point, but just to go over the top level, it's a 6.6 meter space telescope, the successor to the Hubble and Spitzer space telescopes, demonstrator of deployed optics. I'll show you that in a little bit. There are 4 instruments covering 0.6 to 28.5 microns. The telescope is passively cooled to less than 50 Kelvin, and it was launched on Christmas Day 2021, just 34 days ago. It is designed to be complementary to large telescopes on the ground, ALMA, Roman, and Rubin. It is a joint project of NASA and the European and Canadian space agencies, very important partners in our mission. I work at the Goddard Space Flight Center. The prime contractor is Northrop Grumman. Operations are done at Space Telescope Science Institute. And Eric already mentioned our senior project scientist, Nobel laureate John Mather. So in the last year before launch, we did our final deployment tests of the spacecraft and observatory on the ground. This shows the final deployment test of the sun shield and the tensioning that separates the 5 layers. In the past summer, we packed it up into the launch configuration shown here, and we then shipped it out to the launch site, Kourou, French Guiana in South America. To ship it, we put it into the shipping container and loaded that onto a ship, the MN Calibri, which left Los Angeles for a almost 2-week passage through the Panama Canal. So at the lower left, you see the MN Calibri with Webb inside going through one of the 3 locks in the Panama Canal on its way to the Atlantic Ocean. And then in the lower right, there is the arrival in Kourou, French Guiana for the launch. This picture on the left is humans' last view of Webb directly as the payload fairing, or the fairing of the rocket was lowered down onto Webb, the payload, and the rocket was then moved out to the launch pad on the rails that you see on the right.
10, 9, 8.
This is now the launch video,
5, 4, 3,
and I hope you can hear the sound.
unité, top.
And we have engine start.
We have the launch.
And
Allumage
liftoff.
EAP, décollage.
Decollage, liftoff from a tropical rainforest to the edge of time itself. James Webb begins a voyage back to the birth of the universe.
And then at about 30 minutes after launch, we have this beautiful high-resolution video of Webb leaving the rocket fairing. This video is provided by the European Space Agency and Ariane Space, who gave us such a perfect launch. What you see is Webb moving away from the fairing, and of course in the upper right, that's an image of the Earth, and the body of water there that you see is the Gulf of Aden on the northeast coast of Africa, because in just 30 minutes, Webb had gone across the Atlantic and across Africa. As you see Webb going off into space, it lined up such that the sun was reflecting right back into the camera. And then at about a minute after it was released, that beautiful deployment of the solar array. This is the point at which in the Mission Control Center there was wild cheering, because we all knew that with that solar array going deployment, we will have power for the rest of the mission, and that solar array is now working very well. So to go through the next 34 days of what's happened on the mission, there were 50 major deployments. They have all been successful. There are 178 release mechanisms, and every single one of them worked. We saw the solar panel deployed, which is now providing 3 kilowatts of power for the mission. The high gain antenna has been deployed, turned on, and is in use. We need that to send down the science data from the observatory. And the mid-course corrections to insert us into the correct orbit have all been very successful. One extremely important deployment was the deployment of the Sun Shield, which included 140 release mechanisms, 70 hinge assemblies, 8 deployment motors, 400 pulleys, 90 cables totaling 1,312 feet, and every single thing worked perfectly. You can see in the video that the mid booms are being extended to pull out the solar, the sun shield, and then the tensioning that separates the 5 layers so that they can be each successively colder and allow the telescope to cool. As you'll see in a minute, we have indication that the sun shield did actually work. The deployments were pretty much perfectly. And then the final major deployments was the telescope. The secondary mirror came out. There's an instrument radiator to keep our cameras nice and cold, and the 2 side wings of the primary mirror. Following the major deployments, we then had to move the secondary mirror and the 18 primary mirror segments off of their launch snubbers. We moved each of them a total of 12.5 millimeters at the rate of about 1 millimeter per day. So that took about 10 to 12 days. And that's all been successful, and the mirrors are now in position for this next step, which the next speaker will tell us about. Meanwhile, astronomers around the world are observing Webb from the ground. Webb is reflecting sunlight off its sun shield, and it has been bright enough to be detected by backyard amateur astronomers and by university telescopes. As Webb's orientation changes, the amount of sunlight being reflected back to the Earth can vary by up to a factor of 100 times. Webb was featured in 2 Astronomy Picture of the Day posts. On the left, there is the launch of Webb, the launch plume with Comet Leonard in the background. This beautiful picture. And on the right is a time-lapse image of Webb as it moves across the sky. That's an animated GIF. If the video resolution isn't good enough, you can get that from the Astronomy Picture of the Day, December 31st, 2021. People are also taking light curves and have found that Webb's light curve is repeatable. On the left is a University of Hertfordshire Bayford-Bury Observatory light curve. There's actually 2 light curves taken 8 days apart, and showing the big change in magnitude between the brightest and faintest. And then on the right, Peter Plavchin of George Mason University took a light curve of JWST and flipped it in time, showing that the light curve is very symmetric and repeatable. What's happening here is that for some of our spacecraft activities, calibration activities, we put the observatory with the solar array pointed at the sun and then spin the spacecraft around that axis on a 6-hour rotation schedule. As it turns around, sometimes the sun shield, which is not flat, it's got some bends in it, the sun shield reflects the sunlight directly at the Earth, kind of a glint, and then at other times it's more diffuse light. And so that's what's causing the light curve. Once we start pointing the telescope at astronomical targets for the next step of phasing the mirrors, we won't have this sunline rotation quite as often. So the light curves will be a little bit less interesting. Meanwhile, the observatory is cooling. All of our primary mirror segments are now below 80 Kelvin. Our mirror is colder than the operating temperature of Herschel, and the secondary mirror is at 34.7 Kelvin. We still have some heaters turned on in the instruments, and we are in the process of carefully cooling down the instruments through the water band. So when Optics in a vacuum are between 140 and 160 Kelvin. Water can condense and freeze on the optics. So we want to keep everything at about the same temperature. MIRI is thermally isolated from the other instruments, so that goes first, and then we keep the near-infrared instruments using heaters at about the same temperature as MIRI. Soon, however, we'll be through the water band and we'll turn those heaters off, and the instruments will then cool down to the point where we can start to use them. If you'd like to follow along with Webb, we have the Webb blog posting once per week, and that's at blogs.nasa.gov/web. We also have the Where is Webb page, which shows you what we're doing at the moment. That page is now being updated for the next phase of the mission. Back in 2006, we published the science goals and design of the observatory in the Space Science Reviews. And of course, we have our website and all of the various social media channels that you can follow to keep up to date. So I'm now going to turn it over to the next speaker to tell you what happens next in the mission.
So thank you, John. I would now like to invite Dr. Michael McElwain, who is the JWST Observatory Project Scientist at Goddard Space Flight Center, to tell us about commissioning the telescope. Mike?
Great. Thank you very much. Can you see my charts?
Yes.
Okay, excellent. So hi, I'm Mike McElwain. I'm the Observatory Project Scientist for JWST. I'll add to John's presentation that sunline rotation that we were doing was to distribute the momentum across our reaction wheels, our 6 reaction wheels. And so that was the function of that sunline rotation between our major deployments. So in this talk, I'll tell you a bit about commissioning the telescope. So in this chart, you can see on the ray trace on the left-hand side that James Webb is a 3-mirror anastigmat. So we have a primary mirror that's concave, a secondary mirror that's convex, and produces an intermediate focus, a Cassegrain focus. And that was actually important for our test program. We were able to put sources there to characterize the alignment of the science instruments to the telescope and also the telescope itself. The beam then passes on to a tertiary mirror that removes the resulting astigmatism and flattens the focal plane. So we have a much larger focal plane, as you'll see. And each of the science instruments then has a pickoff mirror in that focal plane. So we have the tertiary mirror, a fine steering mirror, and then that focal plane. As John mentioned, the primary mirror is 6.6 meters in diameter. Of course, that exceeded the diameter of the launch fairing and drove the architecture to this segmented primary mirror design. And so Webb has 18 primary mirror segments. Each of those segments has 7 degrees of freedom. So the image at top right, you can see a primary mirror segment with its actuators on the back. There's 6 mechanical degrees of freedom, and we can also correct the radius of curvature for each of these actuators, or each of these segments. And in total, Webb then has 131 degrees of freedom. The secondary mirror has 5 degrees of freedom. And I'll note that the secondary mirror is about 3/4 of a meter in diameter, and so that's about the size of the Spitzer Space Telescope's primary mirror. And the image at bottom right here shows the telescope coming out of the cryogenic testing that we did at the Johnson Space Center. And so a nice picture of the telescope after testing. So the objectives of the telescope commissioning is that we'll be aligning the telescope. That's about a 3-month process that we're planning to begin early next week. And we'll also be characterizing the optical performance of the telescope. So that includes the line of sight, the wavefront static errors. And so after the telescope alignment, we'll have that wavefront static measurement. And then we'll look at the wavefront stability. So as we point within our field of regard, we expect the wavefront to drift, and we'll measure those drifts. We'll be measuring the end-to-end optical throughput, and we'll also be measuring the backgrounds and stray light. So on this next chart here, I'm showing the different stages that we have in telescope commissioning. So as John mentioned, we completed the segment deployments. Each of the mirrors was deployed 12.5 millimeters at the rate of a couple millimeters per day. So that's about the rate at which grass grows. This deployment phase went extremely well. All the actuators are acting nominally, and we have a fully deployed telescope. What we're starting in on next week is actually the alignment phase of the telescope. And so this is a process that we've broken down into 7 steps for presentation, but it's a very iterative process. And so, yeah, this sort of gives a basic description of what we'll be doing. The process actually takes this initial deployment and increases the alignment by about a factor of 100,000. So at the end state, the mirrors will actually be within about tens of nanometers of their optimal positions. And so in order to achieve that, we actually need a number of different control techniques and in these stages. So we have the segment image identification. So when we first deploy the telescopes, they're actually randomly sort of pointed on sky. We find the segments and identify the telescope bore site, the optical axis of the telescope. Then we do the segment level alignments. And then we bring those segments together and actually put them on top of each other. We call that image stacking. At that point, the segments are not phased relative to each other, so there's deconstructive interference. And then we start in on this phasing process, and we have 2 steps there, coarse phasing and fine phasing. The coarse phasing aligns the segments to within about a wavelength, and the fine phasing then brings them to within a fraction of a wavelength. We do that whole process for a single field point, but that actually leads to a degeneracy between a primary mirror error and a primary to secondary mirror misalignment. And so we actually have to then measure the wavefront across the full field and then to break that degeneracy and then align the telescope. And so this process is iterative. And so there are places where we go back and repeat various steps. But at the end, we'll have an aligned telescope. We're also doing this alignment phase while the telescope itself is actually cooling down. So while the wavefront will be drifting from the structure, changing shape as it reaches its operational temperatures. And so that adds an additional layer of complexity. Of course, we've prepared for that. After we've completed the alignment, we'll do a thermal stability assessment, and then we'll be doing monitoring and maintenance over the life of the mission. So this short video shows a cartoon description of the alignment process. So here you can see the segments deployed. They're sort of randomly pointed. Here they're moving we can move them in those 6 mechanical degrees of freedom. This is just showing the actuation. We point to our favorite target. The first target we'll be observing is HD 84406 in Ursa Major. At this point, each of the 18 segments is actually acting as its own telescope. So we need to bring them together and phase them relative to each other. So first we need to locate the segments. Here we're doing the image stacking, bringing the segments on top of each other. That in and out motion of the spots is to ensure the actuators are in the right parts of their range between the coarse and fine mechanisms. And this is showing here a mock point spread function. So you can see the 18 segments coming together, but they're out of phase. And then as we align them relative to each other, we have a diffraction limited optical performance at 2 micron is the requirement and the objective. Okay. So as I mentioned, we do our initial alignment at a single field point. So what you're seeing here is the focal plane of the telescope, and you can see the different science instruments have pickoff mirrors, and so they're actually looking at different parts of the telescope's field of view. And so we initially align the telescope to the single field point, and then we, after that's completed, then we go and look at these other field points across the entire telescope focal plane and do an alignment across the entire field of view. So the team that we have here is well prepared for these activities. And so I have an image here on the left-hand side. The testbed telescope at Ball Aerospace is a 1/6 scale of the James Webb Space Telescope with the same optical prescription and optomechanical control features. And so that was used to demonstrate the wavefront sensing and control algorithms and prove out the software that we're using for flight. Of course, we also did cryogenic testing of the flight hardware down at the Johnson Space Center. And the image up right is showing an interferogram showing that we phased the telescope at the cryogenic temperatures. So we're also very interested in the line of sight. And so we have pointing information from the star trackers that gives us course pointing to about 8 arc seconds, absolute accuracy. We also have a fine guidance sensor within the nearest instrument that controls for fine pointing. And so that gives us better than 1 arc second pointing. The fine guidance sensor also is part of a control loop that drives corrections to the fine steering mirror. And that corrects at low frequencies what the drifts would be. We do anticipate that there's jitter disturbances that will not be corrected. And so the primary jitter that we expect are from the action wheels and the cryocooler exported vibrations. So we do have an activity for the cryocooler, change the pulse frequency while we're monitoring the line of sight jitter, and then to select the optimal frequency there. We'll also be demonstrating our moving tracking capabilities. The requirement's 30 milliarc seconds per second. That's the rate at which Mars moves on the sky. But we'll be testing at rates up to 60 milliarc seconds per second. And that's actually important for enabling observations of some near-Earth asteroids and comets when they're best observed. I mentioned this wavefront stability. That's an important part of our characterization. So while Webb points within its field of regard, either towards the sun or away from the sun, the solar heating on the observatory changes, and we expect that to actually introduce drifts, optical drifts that we plan to measure. Those temperature changes are extremely small, and so they're less than 100 millikelvin for the telescope, and for many of the components, it's less than 10 millikelvin. So we're talking about really small temperature changes, but for the telescope, that does cause a drift. In the worst case, we think that could be 50 nanometers. And so we have an activity set up to do this test where we'll stabilize hot and stabilize cold, watch what the drift is, and measure the various time constants. So at the minutes, hours, and days time scales. We'll measure those amplitudes and time constants. And of course, we don't plan to operate the observatory in this way. We'll be pointing to objects in cycle 1 based on what's efficient for science observations and what's prioritized. But this is an important characterization for what to expect for the wavefront drifts underlying our observations. And then for the life of the mission, we plan to monitor the telescope focus and alignment every 2 days, with the expectation that we can update the telescope, the primary mirror alignment, that is no more than every 2 weeks. So that 2 weeks is actually an important time scale that we're measuring during this wavefront stability activity. So I'll note in this image here, this observatory is not like the other observatories. And so in the sense that the telescope is fully exposed to space. And so that means that we're susceptible to stray light coming from various points on the sky. We're also very reliant on this sun shield to reach our operational temperatures. And so another important component of the telescope commissioning is measuring the backgrounds. And so in many of the modes, for example, the near-infrared broadband imaging. Yes.
You should wrap up now.
Thank you. Actually, I can't see you. But yeah, this is my last chart. And the long wavelength MIRI, the background contributors are actually dominant over the noise terms. And so you can see this plot on JDocs and read more about the background characterization. Thank you, Hashima. And I'll turn it over to Jane.
Okay, thank you, Mike. So our next speaker, Dr. Jane Rigby. She's a JWST Operations Project Scientist at Goddard Space Flight Center. She'll be talking about commissioning the science instruments. Jane?
All right, Hashima, can you see my screen?
Yes.
Great, thank you. All right, so let's talk about how we pick up where Mike left off and talk about how we commission the science instruments to transition into science operations. So this is the big picture overview of how the 6-month commissioning process goes. John talked about the deployment part of that in blue, and Mike talked about in orange, this telescope commissioning part that leads to a fully aligned telescope at about day 120. And so I'm going to talk about in green here the science instrument commissioning part, this 2-month intense period where we check out the science instruments and get them ready for science operations. So let's just for a moment look at where we are right now. Today is this is 34 days after launch. And so we are right here at the end of this gray period between deployment and telescope commissioning. The exciting thing that's happening this week is that we are turning on the science instruments and getting ready to do the wavefront sensing for the first part of the telescope alignment. All right, so let's dive into this green part of science instrument commissioning. So first of all, what commissioning is and is not. So commissioning determines that the spacecraft is working correctly. It also calibrates some part of the spacecraft. It gets the observatory working correctly, and it gets the science instruments working correctly. We need to show that the science instruments are calibratable, that they can be calibrated. We do not calibrate the science instruments during commissioning. Calibration will happen during cycle 1. It's the calibration observations are either in parallel, or if they need to be prime, they're interspersed with the science program. So commissioning gets us ready for science operations. During science instrument commissioning, we'll be checking out all 4 of the science instruments. That's NIRCam, NIRSpec, MIRI, and NIRIS, and all 18 science modes of those 4 science instruments. I want to give you a sense for how this works, a little bit of behind the scenes here. Every step of JWST commissioning is scripted. There's a cast, a huge script that lays out each step of the commissioning process. And so I added them up just to give you a sense of scale here. There are 730-something high-level steps in that timeline, and those get broken down into 10,000 steps that we are methodically stepping through during commissioning. The first 2,800 of those are for the deployments in the spacecraft. We're most of the way through those. We have 5,400 steps for the telescope commissioning that Mike just summarized. And we have about 1,500 steps for the science instruments. So it is this it's this interlocked schedule where each activity has prerequisites that have to be satisfied that we walk through to get commissioning done. And in the background of this and the next couple slides, I have some visualizations of the cast, just showing how we're stepping through activity by activity of those 1,500 science instrument steps. It's not meant to be readable, it just gives you a flavor of how dense the activities are that we have to do. Science instrument commissioning is using the same tools that we're going to use in cycle 1. Each activity is specified through an APT file, and it's run on board in the same way we're going to run science observations with the onboard scripts. To support science commissioning, science instrument team members have flown to the Mission Ops Center from Europe, from Canada, from elsewhere in the US, and will be spending months commissioning their science instruments. I really want to note that huge effort of so many people to get this observatory ready, and just speak on their behalf, but highlight how much work is happening by so many to get these instruments ready. So how do we decide that we're done? So each observing mode has specific quantitative criteria for science readiness that say, okay, this looks ready to go. Doesn't mean it is perfect or that we have, it means that this looks like it is ready to start science operations. The commissioning scientists, that's me, Scott Friedman, and Randy Kimball, we are tracking these criteria as we move through commissioning. And mode by mode, as the criteria get satisfied for each mode, the mode will get formally reviewed and approved as being ready for science. So mode by mode rather than instrument by instrument is how we're going here. It is possible that we will start science operations with one or more of those 18 modes held back for additional work. If we're not happy with it, if we think that that it is not performing the way it ought to be and that we can make that better, we're not going to start science operations with that mode. We may hold it back for additional testing or some additional commissioning activities. So how do we get out of commissioning? So commissioning ends about 6 months after launch, when we are done with the cast, when the science instrument modes have been approved as ready for science. There will be a big public release of the early release observations. These are designed to be on the front pages of media all around the world. At that point, the commissioning data then go public in the archive, all of the commissioning data, the good, the bad, and the ugly, including the EROs. And we start science operations. It's actually possible we may start science operations a couple weeks before, while waiting for the ERO the big ERO release. So, how many years of science operations are we talking about? This is one of the questions from the upvoting. So let me just talk through that. Propellant. We have a level 1 requirement for a 5-year mission life. And we had a level 2 requirement to carry enough propellant for 10.5 years. We now estimate we have enough propellant for about roughly 20 years at least. So why that good news? Why is that a surprise? This is what we had hoped for but weren't sure we would get. Why that surplus? One, really great stewardship of our mass margins by our engineering team meant that we were able to fill our propellant tanks not just to that limit of 10.5 years, but all the way to the tippy top. We also got a great launch date. That turned out to be a good day in terms of taking less energy to get to L2 than many other days of the year. Also, the Ariane 5 gave us exactly the thrust that we requested, whereas what was in the propellant budget was a 3 sigma bad launch. Engineering conservatism. And the mid-course corrections were on time, which means they require less fuel than if they're late, and they were incredibly accurate. So all of that means we have as much fuel as we could have hoped for. So what do we need fuel for? So on board, we use that propellant for the mid-course corrections. Well, we've done 3, they're done. We need them for station keeping the L2 orbit, which is shape that orbit about every 3 weeks. And we need them to dump momentum about every 2 days. The main uncertainty in that is that third one about how frequently we will need to dump momentum out of the reaction wheel. The reason we accumulate momentum is that the sun shield gets hit by solar photons that put a torque on the observatory. And that angular momentum is taken up by the reaction wheels, but then we have to spin those reaction wheels down by firing the thrusters. We will be conducting during commissioning fairly soon an activity to measure the accumulation rate of momentum on the sun shield, and that will give us a revised estimate of how frequently we'll need to dump momentum, and thus a revised estimate on propellant lifetime. But I want to, assuming that that goes well, I think it probably will, we have a very well deployed sun shield, then we are in the case where we have more than 20 years of propellant on board. And so in that case, the science lifetime of Webb is likely not limited by propellant, but rather by the lifetimes of the key parts of the spacecraft and the science instruments. So my last slide here, we are preparing, the whole point of science instrument commissioning is to get us ready for transformative science. And with that very healthy propellant budget, we are looking at many years of transformative science with Webb. This is a picture of Webb. The arrow is pointing to a picture of Webb seen 2 nights ago from Keck with the LRAS instrument at its new home at the second Lagrange point. So thank you so much for being part of this journey with us.
Thank you, Jane. We've kept the time exactly. Now we come to our last speaker, Dr. Klaus Pontopod. He's the STSCI JWST project scientist at the Space Telescope Science Institute, and he will tell us about the JWST Cycle 1 Science Program and of the Cycle 2 program and beyond.
Right. Okay, so I'm going to start where Jane left off and talk about what happens after commissioning normal science operations. So here we have the nominal Cycle 2 timeline based on the launch, and you can see where Cycle 2, the call for proposals as well as the deadline for that ends up in this. So as Jane mentions, we start science operations right after the end of commissioning at L+6 months. At this time, we can start observations from all three major categories of science programs, the GTOs, the GOs, and the early release programs. At 3 months, or at L+9 months, 3 months into science operations, we have the deadline for the guaranteed time observation. So it's set there so that those observations will, or that plan will be available for general observers as they prepare their Cycle 2 proposals. The Cycle 2 deadline will be nominally at launch plus 13 months. And so if we assume a nominal commissioning timeline for planning purposes, you can assume that that is in January of 2023. Now, the exact date has not been set yet, and those final dates will be set in the summer of this year in consultation with the JWST Users Committee. And then we can be ready for Cycle 2 to start at the launch plus 18 months for a 1-year Cycle 1. All right, so how do we develop the actual science operations observing schedule? So we thought we'd go into a little bit more detail about that. So this is for normal science operations. So what generally happens is that a program coordinator, or a PC, will work with a PI for the science programs to develop flight-ready observations, right? And those of you who are already involved in Cycle 1 programs probably know this process well. And so the purpose of that is to finalize the observations and resolve any outstanding technical issues with the observations. And of course, if you minimize the observing constraints, there are of course sometimes the observing constraints that are driven by science, but in general, if you minimize the observing constraints, you can maximize the number of opportunities you have to have your program and your visits scheduled on Skype. At that point, then all flight-ready observations can be combined into what is called a long-range plan, or an LRP. This long-range plan takes all the observations and then can allocate possible plan windows for individual visits. And then these observations may be, there might be observations that can be pulled forward if opportunities arise, but you can consider the long-range plan as sort of a nominal plan. The actual observing schedule, which is different than the long-range plan. A long-range plan is just windows where your observation may happen. The actual observing schedule is set by what's called short-term scheduling, STS. So each short-term schedule covers 1 week. And this 1 week of actual scheduled observations is what gets uploaded to the observatory for execution. So these are observations that are then drawn from the long-range plan. The construction of the short-term schedule starts 10 days before the sort of execution week begins. And then nominally, each short-term schedule is uploaded to the observatory on Sundays and will then start executing at midnight Eastern time. So the short-term schedule may, of course, be interrupted for any kind of unplanned events, and so unplanned events can include any kind of rapid target of opportunity observations that were approved in Cycle 1, or it could be director's discretionary observations. All right, so what is the current status of scheduling for Cycle 1? Well, so it's important here to note that the 2-year JWST ephemeris, so the orbit, is required to develop the long-range plan. And this only became available after the mid-course correction burn number 2, MCC2, which just happened a few days ago. So this work of actually scheduling cycle 1 is only now starting. PCs, program coordinators, also resolving some final issues in a small number of programs. So you can expect that an initial long-range plan will be constructed during the months of February and March. And then a final long-range plan will be available in March, and we anticipate delivering plan windows to PIs of programs around mid-April. In this construction of the long-range plan, there are not many high-level prioritizations in terms of programs. What we can note is that the early release science programs will be prioritized to execute in the first 5 months of cycle 1, right? Because that's the original reason for the early release science program, was to have these observations available to the full community at the time when you have to write your proposals for cycle 2. But all other observations, general observer and guaranteed time observations, are equally prioritized in the long-range plan, with the goal to maximize observing efficiency, while of course meeting the program science goals. Also to note is that cycle 1 is oversubscribed by design. We don't want to get to the end of cycle 1 and then not be able to schedule programs. So it means that there is a sort of a tail after the nominal end of cycle 1, or after the nominal end of that 1 year, so L plus 18 months, where there will still be formal cycle 1 programs executed. So it means that many PIs will receive plan windows that are normally in cycle 2, also between July 1st, 2023 and July 1st, 2024. So since the LRP is built for telescope efficiency, the plan window assignments will generally be final. And so if you feel that you have a change that is required scientifically, that has to be requested through the Telescope Time Review Board of the TTRB. And it's the only way to do it. All right. I just wanted to also remind people about the user committee. So the JWST Users Committee is your interface with the mission during science operations. It is chaired by James Bullock at UC Irvine, and they have regular meetings. Let's just remind you that presentations to JSTOC are public, and they're generally available on the URL seen here. And I'm also listing here the current members of the JSTOC, and so you feel free to contact any of them if you have any concerns about science operations with JWST. Also, we recognize that a lot of people are starting to think about their data analysis, and these are exciting times. So just to point you to places where you can get started on your data analysis preparations, you can go to the overall website here. That is a page that contains links to a lot of the resources and documentation. There is the JWST calibration pipeline, which processes raw JWST data from all the science instruments and FGS. This is an open source environment available on GitHub and documented on JDocs and Read the Docs. There's also tools for what you do after you've calibrated your data called the post-pipeline data analysis. And so this includes analysis software, visualization tools, example Jupyter notebooks, and things like that. It's all written in Python and will generally work with AstroPy. We also have a number of simulated science data. About 20 simulated data sets are available for all the science instruments. And then finally, there are a lot of recorded tutorials that were recorded as part of the JWebinar series. Data reduction and analysis tutorial videos are available on YouTube, notebooks. And then we want to advertise, there's a number of community JWebinars set up to take place during commissioning. 4 in total. These are hosted by some of the early release science teams, and you can see the list here. So the registration for the first one, hosted by the Sears team, is open and is scheduled for late February. And with that, I just wanted to leave up this final slide here with with links of how you can keep up to date as a scientist, as an observer, with news relevant to science operations in general now and during regular science operations. Thank you.
questions that were put in the portal. I will go through them in the order that they were upvoted, and they will be answered by the speakers. So the first most upvoted question, and there was a related one lower down. I will combine the two and paraphrase them. That will NASA consider changing the name of JWST? There is a precedent for changing the name of a mission, such as that for SWIFT, which was renamed the Neil Gehrels Space Telescope. So, Eric, would you like to take this one?
Sure. This question has come up earlier this month in the NASA Town Hall, and so I'll repeat what was discussed then. Now, the NASA History Office conducted an exhaustive search through the currently accessible historical archives on James Webb and his career. And they also talked to experts who had combed through those archives prior to the COVID restrictions on getting in them. With those data in hand, the NASA administrator has stated that the agency found no evidence at this point that warrants changing the name of the James Webb Space Telescope. And so that is NASA's position now, and this team here is focused on making that observatory work as best it can.
Thank you. And of course, SWIFT was renamed in honor of the principal investigator, Neil Gehrels, who passed away in 2017. Okay, so the next question is again for Eric. The provided funding for GO, which is the Guest Observer Program Cycle 1, projects was significantly under request, even after NASA extended funding. Will this improve?
This is a learning process for all of us here, both the agency and the community, on how they will work with Webb. I will say that the money that's in there now, which is $60 million a year, it is by far the largest GEO budget that the Astrophysics Division has, more than double that of the Hubble Space Telescope, which was previously the biggest one. That was thought to be about the ballpark figure based upon some studies done earlier by the JWST Advisory Committee. And so we will learn over the next couple of years just what it takes for the community to get science out of Webb. But right now, it is the best funded GEO program that we have.
Thank you. So next one is, I think, for Klaus. What is the rationale for which programs, such as the ERS versus GTO versus GO, get prioritized in this schedule? Klaus?
Sure. So as I mentioned, the only type of program here that gets any special priority is the ERS programs to be executed within the first 5 months of science operations, where we'll do our best to get most of the great majority of them done within those 5 months. And the purpose of that is to make sure that folks can use that data to base Cycle 2 observations on. The GO and the GTO programs are scheduled with equal priority throughout Cycle 1.
Okay, thank you. The next question is rather ambiguous, so I'll, when is Ed going to submit the question? So I'll go on to the next one, which I think is also for Klaus. Are there any plans to streamline the current cumbersome budget request process for GO Cycle 2, or at least provide useful guidelines?
Yeah, so it's a good question. All of this is as Eric says, it's a learning process. The budget process is something that we're continuously discussing with the JWST Users Committee. That's where the main discussion happens. And so discussions are ongoing for how to improve that process for Cycle 2 with the Users Committee. Stay tuned for that.
Thank you. The other one, next one for you also. Any update on when GEO Cycle 2 proposals will be due?
Sure. So as I mentioned, right now, assuming a nominal commissioning timeline, we're anticipating that the deadline for Cycle 2 is in January 3, but the final date has not yet been set and will be set in consultation with the.
Thank you. So the next two questions are not relevant to JWST. What is the airspeed velocity of an unladen swallow, and are you suggesting coconuts migrate? So we'll go to the next question. What do you believe is the biggest technical risk that could shorten or end the usefulness of the JWST mission? Would Jane or Mike like to take this one?
Sure, I'll start answering that question. So as you heard today, we've successfully completed all of our major deployments, and so that, of course, retired a lot of our mission risk that we got through those deployments, but we're still only at L plus 34 days right now, and we have a long way to go in commissioning. So you heard that the telescope mirrors were deployed, and all those actuators are acting nominally at this time, but we need them to align the telescope as I described earlier in my talk. And so, of course, we need them to continue functioning nominally. The mission hardware has been designed for 5 years, but there's reason to expect that the hardware would last far longer than that. The Chandra telescope is a good example of how long these space telescopes can last. And finally, also that most of our components, we have redundant systems in place. So we do have a backup systems in case one of the components fails. We also have the ability to maintain some operations even if we have some degraded performance. So I'll leave it at that and turn it over to Jane. I thought Jane did a great job of talking about mission life. Maybe you have something to add?
It's hard to add to that great answer other than just to reiterate that we're now in a stage, assuming that the propellant situation, that we have enough propellant, that we're in this stage where the lifetime is likely limited by the lifetimes of key parts of the spacecraft and the science instruments.
Thank you. So the next question is, what is the brightest, warmest object JWST can study without risk to the instruments? Jonathan, would you like to take that one?
Sure, thank you. So first of all, I want to say there's no danger to the instruments by pointing at anything on the sky that Webb can point at. So even if we point at something that's too bright to get useful data, there's no danger or no risk to the instruments. However, some things are too bright, so the detectors would saturate and we can't get good data. But the brightest thing in our plan currently is the planet Mars. And we are planning to observe Mars with some narrowband imaging and spectroscopy. Lots of good science will come of that. The brightest target star in Cycle 1 is Gliese 357, which is a 7.3 magnitude star. And it's a star that has a transiting super-Earth planet that we will be studying. We may do coronagraphic observations of debris disks around some brighter stars. And there's also a 4th magnitude star that's in the calibration plan. That star is Delta Ursa Minor, 4th magnitude. It's the next star down from Polaris in the Little Dipper, which is kind of fun. It's not a science target, but we'll be using it for calibration. But again, no risk to the instruments, but these are some of the brightest objects that we'll be studying scientifically.
Thank you. The next one is for Klaus. Why not set GEO grant award amounts using a fair share model like Chandra, XMM, and Spitzer? It's fairer and less work.
Right. So during Cycle 1, the process was set up and as it will be in the future. Again, by discussions with the Cycle 1 Grants Task Force, which was a committee that was instituted by the Users Committee. And they discussed this, and they discussed the equity issues as well. And the clear recommendation we got from this committee is that it's actually more equitable to have had the review for Cycle 1 for a number of reasons. Like one, for example, was that the JWST is an international collaboration, and we are only awarding, NASA is only awarding funds to U.S. investigators. And so the review has allowed us to look at the relative work between ESA, or European-based Canadian, and U.S. investigators. They were also concerned about the equity for young researchers and teams, early career researchers. So issues like that made it important for us to hold this kind of review. Now that was for Cycle 1. So that doesn't mean that we're going to necessarily fix that process for future cycles. And again, this will be a very close discussion with the user committee. So any concerns you have, please take it to the user committee as well, and it will be taken into account in this discussion.
Thank you. The next one is also for you. Will commissioning data be made public after the commissioning phase, for example, PSF, etc.? If not, why?
How about I take that one, Hashima?
Okay.
All the commissioning data will be made public after commissioning is over. That includes all of those bright stars with the wavefront sensing. It includes the background measurements. All of that commissioning data will be in the archive and public after the early release observations are publicly released. A lot of that will not be interesting for science, but some of it will be.
Thank you.
And I should add that to interpret all that data, we are preparing updates to JDocs on what we've learned about in-orbit performance and trying to get that out to the community as quickly as possible so that as users, we can understand, what is the actual performance, and that will also help interpreting the commissioning data as well as the Cycle 1 data.
Thank you. 18 people have sent their congratulations, so I'll convey that to the team. Thank you. Next one is, I think this will again go to Klaus. Is there any ranking of the GO programs that can influence whether they will be observed in Cycle 1 or moved to Cycle 2? Klaus?
Yeah. So no, there is not. Once you've been accepted for inclusion in Cycle 1, all the same priority. There's absolutely no prioritization done in that way. The visits are scheduled solely based on the constraints that were submitted with the proposals, along with observatory efficiency.
Okay, thank you. Next one, I think, is for Jonathan. Are there targets that researchers may want to observe but can't because of JWST aiming and L2 orbit restrictions?
Okay, thanks. Webb can observe any fixed point on the sky at least once per year for at least 51 continuous days. So there's not anything on the sky any fixed object on the sky that we can't look at least once per year. The Webb can observe 40% of the sky at any given time, and that is called the field of regard. It's an annulus going from 45 degrees to 95 degrees away from the anti-sun direction. Now, within our solar system, Webb cannot observe Mercury, Venus, the Earth, or the Moon because we can't point towards the sun. But we can observe anything from the orbit of Mars on out and anything moving up to 30 milliarc seconds per second, which does include Mars and comets and asteroids that are of interest. And as Mike mentioned earlier, we are going to test whether we can observe things that are moving faster than 30 milliarc seconds per second relative to the fixed stars. But the basic answer is that yes, we can observe anything on the sky. Sometimes we have to wait a little bit until it comes into our field of view.
Thank you. The next question is for Eric. Is there any change or plan in the proprietary period for JWST, GTO, and GO programs, current and future cycles?
So the exclusive use period or proprietary time was set many years ago and is in the Memorandum of Understanding of an agreement between NASA, the European Space Agency, and the Canadian Space Agency. And it was set to 12 months, which was fairly typical when this was all being formulated. Now, in that MOU, there is also a stipulation that the Institute director can propose changes to that time as people begin to get experience with the observatory. So that's a possible change that could happen through that mechanism. Many people waive their time already, that exclusive use period, and for larger programs, there's typically no exclusive use period for those as well. So in this first cycle, for example, there are many, I think, thousands of hours that are already no exclusive use period with them. And we know that's the direction that NASA is at least moving, but we will have to wait for this mechanism where the Institute director more or less confers with the community to see how it's gone at least the first year.
Thank you. How much of cycle 1 is oversubscribed as fraction of cycle 2 time, and how did this impact underfunding of cycle 1? Will this be taken by Klaus?
Yeah, I can take a stab at that. So cycles are roughly oversubscribed by 25%. But it's important to keep in mind that cycle 2 will have a similar case, right? Because it's just a moving window, right? So for cycle 2, you also want a tail because you don't want to run out of observations at the very end of that year, and cycle 3 and so on. So there's not really any kind of special consideration for cycle 1 in that context. That answers the question.
Okay, thank you. Just looking, going through that. How accurate or powerful is the JWST? If it was pointed at Mars, could it spot the tiny Mars rovers? Other examples? Thanks. Jonathan?
Sure. So we will be observing Mars, but the spatial resolution on Mars of the Webb telescope is not good enough to see something as small as the Mars rover. Webb was designed to see very faint things and to get very clear pictures of the sky, but not quite good enough to see an object as small as the Mars rover on the surface of Mars.
Thank you. Will there be a JWST live where we can see what JWST is looking at, like for HST? Jonathan? Not sure what you mean for. Yeah.
Yeah, I believe that there is a plan for that after we move into science operations. That there will be a website that reports what Webb is observing at the particular moment. That won't happen during commissioning, but will happen then later in the summer when we move into the science operation phase.
Okay, thank you. What instruments are turned on? Have any photons been recorded? I think the answer is no, but Jane?
I think we'll be ready to talk about that in a day or two.
Thank you. Now that JWST has launched, when will DDT, I think they mean Director's Discretionary Time, proposal submissions be accepted? Klaus, do you know the answer to that one?
Yes, I do. So that is something that's being worked on. There's some documentation that has to be done, checking performance during commissioning and so on. But the plan is to have that possibility available at the beginning of cycle 1. And so you should anticipate, and once cycle 1 starts, you should be able to submit DD proposals.
Thank you.
And it'll presumably be a similar. I just wanted to add to that a little bit, Hashima, that it's similar to Hubble, and there needs to be a compelling reason why the proposal couldn't wait till the next cycle and couldn't have been proposed in the previous cycle, right? Why it's so timely.
That's right, Janie. It'll be very similar to.
Okay, thank you. Whereas Webb says that the cold side has been at minus 203 degrees centigrade since the sun shield was deployed. Will it get much colder than this? Mike?
Yeah, so John Gardner presented a temperature map on the primary mirror segments. We can actually read the temperatures for each of those segments. And if you go back to the recording and take a look at what's reported there, you'd be surprised to see that the center segments are a little bit warmer than the bottom one close to the spacecraft bus. And there's actually a reason for that, because we currently have the fine steering mirror heater still on, and a heater for the science instruments are still on as well, as John Gardner mentioned in his talk. And so we plan to turn those off pretty soon, at which point the temperatures will cool off and reach their equilibrium temperatures. We expect on the primary mirror those temperatures for those segments to reach between the range of 35 Kelvin and 50 Kelvin. For normal operations, the segments, the spacecraft bus, which is of course a heat source, are going to be the warmest.
Thank you. How long are the reaction wheels projected to last? Jonathan or Mike?
I could take that one as well.
Mike.
Yeah, so we have 6 reaction wheels. They have heritage to the Chandra X-ray Observatory, and so Chandra's been operating for over 20 years. There's actually a test program for the same reaction wheels that we're using at the Marshall Space Flight Center, and that's actually been running for over 24 years now without any faults or anomalies. So we think that those wheels are very robust and have a very long lifetime. As I mentioned, we have 6 wheels on the observatory. We're prepared to run with 5 wheels. And so we do have some redundant capabilities there as well.
Thank you. Will the images taken by the JWST during the calibration period be published? That is in the next couple of months.
I'll take that. We are currently in the process of determining what can be shared and when, based on the timeline and how commissioning goes.
Thank you. The first year of observations are already selected. What are they? Klaus?
Yeah, sure. So there are almost 400 science programs in Cycle 1. So I'm not going to list all of them. But they're all, you can find information about all of them on the website for scientists on jwst.sdsci.edu. You have to follow a couple of links. You'll find a place called Improved Programs. And there's a nice table there of all the programs, and you can, depending on how much detail you're interested in, you can click through and even download the observing scripts that define all the programs there.
Next one also for you. How much provision is there for repeating failed, for example, due to, for example, alignment or guiding issues, Cycle 1 observations?
So I believe that if there is a provision for that in terms of how much time we're planning with requiring, I think that the number I've seen is 5%. But of course, that's that it remains to be seen what that number actually is. And here we just talk about failed acquisitions and guiding and things like that.
And from the user's perspective, it'll be similar to Hubble. You'll submit a request to say that your observation failed and you need to have it repeated, and here's why.
Okay, thank you. Can you show a graphic of what the JWST halo orbit looks like from the Earth compared to the full moon? 2 times larger, 10 times, question mark.
So I'll take that. I just typed JWST halo orbit image into a search engine and got several graphical depictions of the orbit and how it looks in the frame from the Earth and how it looks relative to motion around the sun. I think that's probably the best way that you can find the information that we have put on the website about that.
Okay, thank you. Can or will JWST be able to expedite pointing for observations of optical signals originating from detected FRBs and especially for repeaters? Jane, would you like to take that one?
Sure. I'll generalize that question a little bit and say that, that's the write a proposal. So yes, we can do observation. So that probably falls under the category of targets of opportunity. So we have a provision to write a proposal where you say, I want to observe this class of phenomena, these kinds of supernova, or this kind of repeating burst. Here are the criteria that would trigger an observation. And you can submit that and get that in approved and then trigger that target of opportunity when an event that is compelling enough occurs. So that is in the call for proposals for cycle 1. We will repeat it for cycle 2. There's also, we talked about earlier, director's discretionary time for things that could not have been anticipated in the routine calls. For something that's truly unprecedented, you can write, and that can't wait for the next cycle, you can write a director's discretionary time proposal.
Thank you. Will early science observations, EROs, become public at the end of the commissioning period? What are the targets?
So I'll take that. The early release observations will be made public at the time that we are showing them at the press conference at the end of commissioning, and the target list has not been made public this time.
What is the best image quality you expect with perfect alignment based on the interferogram from JSC testing? Jane,
So
you want to take that?
I can take that.
Okay.
I can take that one, if that's all right. So our image quality has a very large error budget. One of which, of course, is the wavefront error on the segments themselves. Those are measured very precisely at temperature, but of course that was at under normal Earth-like gravity conditions. We have models that then translate them to the flight conditions. Our requirement is to be diffraction limited at 2 microns, and we expect to have comfortable optical performance against that 2 microns. And we're hopeful that we'll be able to be diffraction limited at 1 micron if everything goes well.
Thank you.
So we will see.
Where will the STSs be posted? Who's going to take that one? I don't know what the STSs are. Okay, next one. Would the telescope be able to function if one of the sunshield layers completely ripped beyond repair?
I can take that one as well. So I think John mentioned in his talk, we have a 5-layer sunshield. So we have 5 separate layers. Each of those are approximately the size of a tennis court, which you've probably heard before. I'll just mention that each layer, if you look closely at the images, they have, it's sort of like a quilted pattern. And so there are separate components to each of the membranes. So we don't anticipate a tear where a single layer would just, tear completely. So there are stops for each of those partitions within each sunshield layer. That being said, we have to meet our thermal requirements, we only need 4 of the layers to function. So right now, beginning of life, if we only had 4 layers, we would still expect to be able to meet our requirements. And so that 5th layer was somewhat for redundancy. And I'll just add that we do anticipate the sun shield to degrade over the life of the mission. So the environment at L2, of course, has micrometeoroids. And we do expect that the sun shields will be degraded by micrometeoroid impacts with small micro tears. And over the life of the mission, our thermal performance will be compromised.
Yeah, thank you. Next one for Klaus.
I'll just the final statement is our models predict that we have certainly that degradation is accounted for at end of life. And we anticipate to have, still meet our requirements after the 10 years that we've planned for. Thanks.
Next one for Klaus. Please point out most current docs on JWST data pipeline procedures and software references, attempting to try personal analysis.
Sure. Yes. So I had a slide in my presentation that has links to that, and so all the presentations will be posted on the event page. So it may be easiest for you to go there. Apart from that, it's worth noting that the JWST calibration pipeline, data analysis tools, these are all open source software environments. For the calibration pipeline, the documentation is very much a living document because it gets updated along with development of the pipeline on Read the Docs. And so, yeah, it should be straightforward to find, but, wait for the presentations to be posted and follow the links there.
Yeah, thank you. Once telescope is aligned, will these coarse and more extensive processes ever need to be repeated? Or is it just the fine alignment tweaks depending on the target? Mike?
Yeah, so for the life of, after we complete that alignment phase that I presented, the plan for our maintenance is to not go back and realign the telescope. We'll just do very small tweaks to the primary mirror, and we never anticipate to go back and redo that alignment process. And I'll just note that the secondary mirror position relative to the primary is important because if you change its position, you change a lot of the calibrations of the plate scales across the science instruments. And so the plan for the duration of the mission after the alignment is just to do the minor corrections on the primary mirror within that fine range.
Okay, thank you. Can instruments be initialized in parallel? Is that one of the observing modes that will be tested during earlier activities? Jane?
Sure, I'll take that. Yes, we support a number of parallel observing modes with 2 instruments at a time. And that is also something that exactly we will be testing those parallel, we will test parallel operations during commissioning. So yes, absolutely.
Now, thank all the speakers once again. And thank you for answering all the questions. And I would like to thank all the attendees for their attention and for all the interest they have shown in posting questions. And that shows the large interest that the community has in JWST and everyone looking forward to the groundbreaking science that JWST will deliver. So thank you once again, and I would like to thank the staff of STSCI for hosting this town hall. So thank you.